In the past couple of videos, we learned how to use Newton's method to find the roots of polynomial functions. Then, we shifted our attention to sinusoids and explored how to find their intersections with other types of functions. After that, we demonstrated how Newton's method can also be applied to logarithms. In this video, we will focus on quadratics. Our goal is to find the square root of any number without using a calculator. To do that, we will turn the square root problem into a root finding problem and then apply Newton's method. Before we begin, if you are not familiar with how Newton's method works, I recommend watching the previous two videos in this series. The Newton's method playlist can be found in the top right corner of the screen or in the video description below. First, let me ask you a simple question. Do we know the square root of 4? We should be able to recall that it's 2. Now how about the square root of 9? We know it's 3, right? But what if we are asked to find the square root of a number between 4 and 9? We know the answer must be between 2 and 3, but without a calculator, we may not know its exact value. In this first example, we will focus on finding the square root of 8 using Newton's method. Let's square both sides of the equation. Then we can rearrange the terms. So, finding the square root of 8 can be turned into a problem of finding the roots of this quadratic expression on the left-hand side. This left-hand side is now our function of interest. Let's sketch the curve. It's a quadratic curve that intersects the y-axis at -8, but we don't yet know exactly where it intersects the x-axis. Next, let's differentiate the blue function to get its derivative. Now, let's recall Newton's method. We can substitute the expressions for the function and its derivative into the formula, which gives us the iterative rule that we need to use. Now, we want to apply Newton's method with an initial value of 3.8. Let's carry out the iteration one step at a time. It looks like we're moving smoothly towards the root. And by x4, we have already converged. So 2.828 is the root, and this is the answer that we were looking for. This means that squaring 2.828 gives us approximately 8, and now we know the square root of 8. Next, let's run the iterations again, but this time using an initial value of minus 3.8. Just like before, the method progresses quite smoothly and gently. There's not much instability. This time, we eventually converge to negative 2.828, which is the negative version of the answer that we found earlier. When we solve x squared equals 8, there were two possible solutions, a positive one and a negative one, and this is the negative solution. Now, let's try a different initial value of 1.2. What do you think will happen here? Will the method fail to converge? Will it become unstable? In the first step, it overshoots the answer pretty dramatically. But from there, it moves back smoothly and gently toward the positive root. For this quadratic function, the minimum point is also the y-intercept, and the curve has two roots. If our initial value is on the right side of the y-intercept, we converge to the positive red root. If it's on the left side of the y-intercept, we converge to the negative orange root. Unlike some of the previous examples, there's no catch here. There's no invalid results, no severe instability, and no strange behavior, as long as we don't choose an initial value of 0. The only interesting situation happens when we shift the curve upward until it no longer has any x-intercepts at all, and therefore it doesn't have any real roots. If we apply the version of Newton's method we learned so far, it's gonna fail, because the curve doesn't have any roots, at least not any real ones. In this case, we're effectively trying to find the square root of -1, which has no real solutions. But we can handle this by applying Newton's method in the complex plane, which is illustrated over here. By doing that, the method can converge to complex roots when the function does not have real roots. And this is the topic we're gonna explore in the next video of this series. But before you move on, please consider liking, commenting, and subscribing to support the channel so that I can continue making content like this in the future. If I've already made the next Newton's method video, it should be on the screen right now.